now it's time to step back and evaluate everything we've just gone through. So we'll talk about the pros and cons of this approach using parallel streams. So first thing to note, no big surprise, the parallel streams version is substantially faster than the sequential streams version. Not a big surprise, but it's worth noting. And as we talked about before, it doesn't give you as much of a linear speed up as other more CPU-bound programs might do, like the ImageStreamGang program that search for the phrases in the complete works of Shakespeare. And that's because this is an I/O-bound program, so there's going to be a lot of sharing of things like the file system, like the network, and so on. So even though we're getting a win, it's not an n-fold win where n is the number of cores. And the reason, of course, we do get this speed up is because the images are downloaded and processed in parallel on multiple cores. And also, as we've talked about before, we use this clever technique of the common fork join pool using the managed blocker stuff. So it'll expand the fork join pool, common fork join pool as needed to keep things humming along at full tilt. The other nice thing about this is the solution is relatively straightforward to understand, once you understand streams, of course, and parallel streams. But it maps quite nicely onto the domain intent. So basically, you say, download images that aren't already cached, apply filters, print the results out. So it's pretty much a one-to-one mapping. Another nice thing about this that makes it easy to understand is the behaviors are all synchronous. They're all two-way calls, request-response. So checking to see if it's cached, that's a synchronous call. Downloading the files, that's a synchronous call, meaning it doesn't come back until we're done. The call does not come back until we're finished. Applying the filters, again, transforming, storing, all done synchronously. We can pretty much understand that by understanding two-way responses. And the reason this works well is because it's parallelized using parallel streams. Another nice thing about this is the flow of control of the program is pretty linear. So we can start at the top and just kind of read it from top to bottom. There's no loops, there's no if statements, there's no switches, there's no go-tos. We can take a look at this from top to bottom, which at least in my mind makes it easier to understand because you can sort of see it in a linear scan from top to bottom, even though it's not running linearly. And in fact, the parallel solution looks identical to the sequential solution. All we have to do is replace parallel stream with stream, same flow, just not running in parallel. But of course, not everything is unicorns and rainbows, as I like to say, so there's some things that could be improved. The most obvious of which is completable futures can be faster. So there's clearly, we're giving up something. This wonderful, clean way of doing our processing with parallel streams has a potential downside that we could do better. And in general, what you discover, not always true, but often true, completable futures are usually more efficient and scalable than parallel streams, but they're also somewhat harder to program because they require you to understand asynchronous patterns. And we'll talk more about that when we get into completable futures. But as usual, there's almost always a trade-off somewhere, and the trade-off here is between human productivity. It's really easy to write a parallel stream solution, but we sacrifice a little performance, whereas completable futures, a little bit harder to write, but often run a little faster. My advice to you is often try to use the simple thing first, using parallel streams. If it meets your performance requirements, you're done. If it doesn't, then you might consider using the more advanced technique. Or if it's an assignment in the class, then you have to use the more advanced technique. OK, so that's the end. We're done. And I'll see you next time.